connection with post accident cooling of nuclear reactor cores. This is the topic, and we start with Leidenfrost phenomena, which is probably the name is familiar to many of you. And you see the Leidenfrost phenomena, it is very important in engineering, but it was first discovered by a physician, medical practitioner. So, in 18th century, a German doctor of the same name Leidenfrost, he first reported the phenomena. And then the thing comes, which I have told that it is counterintuitive, that let us say there is a surface, and on the surface we have got a droplet of liquid, and let us say the droplet of liquid is at room temperature and the surface is at Tw wall temperature, and this is T. Now, Tw is greater than T. So, ultimately what will happen? The droplet will evaporate. Now, what is counterintuitive here, that there is a time for evaporation of this droplet. If Tw increases, then people find that the time of evaporation that also increases, which is counterintuitive. We know that as the temperature difference increases, there will be more heat transfer and quickly evaporation will take place, but that is not the case in this particular phenomenon. So, the droplet evaporation will get delayed as the wall temperature increases. So, that is the first uniqueness regarding rewetting phenomena. Then I will start with something else. Let us say I will go to some video from YouTube. You know, one book of physics is very well known, at least in our time it was there. I do not know till today whether people are following that book, particularly for IIT entrance, that is the book of physics by Resnick and Halliday. So, later on another gentleman, another professor of physics, he joined, he is J. Walker. Now, J. Walker made, I mean that is his motto, to make physics very popular, and he has got many kind of efforts or endeavors for that. One of that is a book called Flying Circus of Physics, and under the name of Flying Circus of Physics there are different entries in YouTube. So, I like to show you one entry.
Welcome to the Flying Circus of Physics. I'm Gerald Walker, professor at Cleveland State University. I'm going to show you a stunt where I've been badly hurt. Don't you dare think about doing this at home, because you could be badly burnt. This is molten lead, 400 degrees Celsius, 750 degrees Fahrenheit, really hot. Let me show you. It's really hot.
What is this? This is a sausage he's putting in the.
Yeah, I'd say that's really hot. Now, I'm going to do something stupid. I'm going to stick my fingers into that molten lead. But first, I'm going to wet my fingers and hope that the Leidenfrost effect will save my fingers. When I go in that effect, the water will immediately vaporize and set up a gas layer on my fingers, keeping the molten lead away from me. At least that's the theory. The danger is if I go in with too much water, there'll be too much vaporization, and that will blow the lead all over my face. I'm kind of excited. Let's try it.
So, he is putting his hand inside molten lead, which is 400 degrees Celsius. Nothing has happened. So,
1, 2, 3, 4. Ha! It worked.
Okay.
Thanks for watching. See you next time.
So, you know what has happened. Many of you know that as soon as the water that is coming in some sort of a surface, or in this case the liquid which is so hot that there is a vapor layer. Kya ho gaya? And the vapor layer is in between the the vapor layer is in between the liquid metal and the well কি হলো So, the vapor layer is in between the water and the liquid metal. So, the vapor layer being insulating, there will not be much of heat transfer between the liquid water and the molten metal, and liquid will stay for a longer time. And for that matter, if our wet finger is there, between the wet finger and the liquid metal, there will be an insulating layer of vapor, and there will not be of much heat transfer. So, fingers are protected. Of course, one has to be very fast, the way it has been demonstrated. So, you see the phenomenon that is very important in many of the engineering application, particularly application like quenching etcetera. And down the line in nuclear reactor, when accident takes place, the primary coolant that sometimes drains out, but still the nuclear core there is decay heat and stored heat. So, that has to be cooled, and that is cooled by emergency core cooling system, basically which is injection of water either from the bottom or from the top, and in that case immediately the hot surface will not get cooled because of this vapor formation. And initially the surface was wet, due to accident the liquid has drained out, and then we are trying to wet it. So, it will get rewetted. So, this phenomenon is called rewetting, and this rewetting phenomenon is very important, because if the time delay of between the normal cooling mode and insulated mode of water injection, where water is insulated from the hot surface. So, if the time delay is very large, so within that small period of time lot of catastrophic phenomenon can occur, and that has to be avoided. So, that is why rewetting, modeling of rewetting, assessing of rewetting, and preventing of a larger period for rewetting, that is important. So, one side we have got the fundamental thing, what is your Leidenfrost phenomena, on which I will devote some time, which is in the scale of a droplet or scale of a small patch of liquid puddle over a solid surface. From there I will migrate to the rewetting aspect of nuclear reactor, and some sort of almost to the scale reactor core I will show, which we have simulated and studied the rewetting phenomena. There are many issues when we go to the large scale that we will see. The Leidenfrost phenomena, the way I have explained it. So, you see this is the droplet and this is the hot substrate, and there will be a vapor layer. Now, this is very exaggerated over here to make you understand, but it is not this exaggerated. So, there will be very thin vapor layer, by naked eye you cannot make it that there is a vapor layer, and the liquid droplet will be almost levitated. For all practical purposes, it will be levitated over the hot surface. Now, we have and now if you leave the liquid droplet on the hot surface, what will happen? So, gradually the liquid droplet will evaporate. So, its mass will reduce. Now, as its mass reduces and at the same time it is floating over some sort of a cushion of vapor. So, then there will be vibration, and due to vibration we can see different kind of shape of the droplet, and these shapes will go on changing. We have some videos, let us see. So, this is the schematic of the experimental setup. This is the hot surface on which we are putting the droplet, and then there are methods of taking photographs, etc., temperature measurement. I will not go into details of it. So, you see this is the way the droplet will go on oscillating, and then of course, it is showing that only one elliptic kind of droplet that is going on oscillating, but as it reduces probably we will be able to see other kind of shapes. Here you can see. So, this is called in the field of vibration, this is called mode switching. So, from one mode of vibration it goes to another mode of vibration. So, there is mode switching, and we can find this kind of oscillation for a single droplet. And as the time passes, we have started with a large patch of water, and then as the patch is very large, so there was vapor generation, and the vapor is coming not only from the periphery, but also from some sort of a vapor bubble formed at the middle, and then it becomes smaller and smaller due to evaporation. Then through the periphery only the vapor can escape, and these are the different kind of shape you can find as the time passes. So, it is a big patch. You see in a big patch how the as I have told that only the periphery is not enough for the vapor to escape. So, vapor has to escape from the middle of the patch also, and we can see automatically how the vapor is being formed, and then it is getting out of this patch, again a new vapor bubble is being formed. So, you see it has got some difference with the classical film boiling. Obviously, it is film boiling, but it has got some difference with classical film boiling. How it is different from classical film boiling? If we see the classical film boiling, the theory whichever is available for a horizontal surface, if we see classical film boiling, just a minute. For a horizontal surface, if we see classical film boiling, so what happens? Let us say this is the liquid, and here the vapor forms on the surface, and at regular interval you will find this kind of vapor dome. There is a theory also how this vapor dome will form. Probably Professor Banerjee has covered some instability mechanism here, and this is your Rayleigh-Taylor kind of instability, probably it has been referred to. So, I have shown one view of it, but in two dimensional plane we will have the vapor domes forming like this, and this is not static. That means, once there will be vapor domes like this, next time there will be vapor dome here, 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 here. But thing is that this pattern, this diamond kind of pattern, of course, which is a square. So, that will be maintained, and there is also a time that will be maintained. So, that is the classical theory of film boiling over a horizontal surface, and from there we can find out what is the heat transfer rate in boiling, film boiling. Now, we were interested that when this kind of patch is there, so infinite expanse of the liquid is not there. So, what kind of theory can be applied here? So, can the classical theory, which is due to Berenson, I believe. So, whether that theory can be applicable here or not. So, this is the theory which I have shown here, I mean which I have described. You can, sorry, just a minute. So, these are the domes through which vapor is escaping, okay. And then you can understand that this area that is supplying for 1/4 and then it becomes a total circle. So, for that kind of vapor generation, this patched area supplies the heat flux. From there, of course, one can determine what could be the heat transfer coefficient. Now, when it is proposed for a large surface extended to infinity. So, whether it is applicable for the small case where there is a limited number of vapor domes, very small patch, only 2, 3, 4 vapor domes are there, and then we can get some sort of a heat transfer coefficient for this kind of Leidenfrost phenomena also. Leidenfrost phenomena and the classical film boiling is to some extent different, because in case of Leidenfrost phenomena, as I have told, the vapor is mainly escaping through the periphery, whereas in this case there are vapor domes through which vapor is escaping. So, then we have proceeded and we have analyzed the surface, and then what we can find we can find that these 4 domes which are forming on the patch, they can be geometrically connected, and when we apply Berenson's postulation and the Rayleigh-Taylor kind of instability. So, the wavelength between them, that is matching quite closely. So, even in this kind of small patch, we can apply Berenson's formula to or Berenson's model to find out the heat transfer. As long as there are vapor dome formation within the patch, when it will become small, it will become a droplet, and only through the periphery vapor release is possible, then of course, there is other kind of theory. So, this is one thing which we have done, and this is another thing as I have discussed, that it will go on different mode switching, and from. So, you see if it is a elliptic kind of droplet or spherical kind of droplet, it will go on mode switching like this. We have made some analysis of this process also, and you see how the fluctuation will take place, okay. Diameter fluctuation, how it will take place, and we have taken a small section, analyzed it, then you see along with the phenomena how we are having the angular position. And then again here there is classically one can find out what is the wavelength, and that wavelength is matching very well. It is taken from the theory of vibration mode switching. For node number 2 there will be some sort of time period, for node 3 there will be some sort of time period, node 5, node 6, etc., and we are getting a good matching with our experiment. So, you see probably not probably, when there is a droplet, it is levitating over the vapor cushion. So, the from classical theory of vibration one can borrow the idea, and one can get what will be the time period, and that matches very well. So, that is another observation we can get from this phenomena. So, this is the frequency, classical hydrodynamics, we can get this frequency. Okay. Then we go to little bit of nanofluid, not much, that if instead of the pure water, if we have got TiO2, titanium oxide water nanofluid, and then if we try to have the Leidenfrost phenomena, what kind of phenomena, I mean what kind of observation we can make. So, you see we have made along with water the other nanofluid solution we have compared, and obviously nanofluid increases the rate of heat transfer and the time for the Leidenfrost droplet to get squeezed, that reduces. But the mode switching phenomena which we have observed in case of liquid water, pure water, the same kind of phenomena is also observed with your nanofluid. I will just cursorily go through the important observation which we have made. So, here we are showing how a nanofluid will ultimately. So, you see what will happen, the liquid will evaporate and a shell of the nanoparticle that will be formed, and due to heat ultimately that will crumble and there is I mean cracks etcetera ultimately, but now what is left is the shell, all the liquid that has evaporated. So, this is how, this is the process through which the nanofluid Leidenfrost phenomena will pass. So, here we are summarizing some of the results, and with nanofluid what is happening, is there any movie? No, there is a movie, let us see this movie. Unfortunately, this is not running, we have lost time, let us not. So, it shows that nanofluid Leidenfrost phenomena is much vigorous compared to water. In case of water, whatever we get, almost at the same temperature we get a different kind of picture. In case of nanofluid, lot of sputtering is there. So, instantaneous wetting of the solid surface, and then of course, the solid substrate temperature is high. So, again de-wetting, again instantaneous wetting. So, those kind of phenomena we can see. Unfortunately, I cannot run the and then what happens, this is interesting, that once the nanofluid totally evaporates, it leaves certain amount of residue on the surface. Obviously, those nanoparticles that will leave on the, that will stay on the surface, and on that now if we pour water, pure water, the same kind of Leidenfrost phenomena we will find what we have found in the nanofluid. That means, the nanoparticle they have a great role in modifying the substrate characteristics. In many other cases, people talk about the bulk properties of the nanofluid, that the bulk property is changed, that is why the heat transfer is changed, but at least in this particular case, the surface characteristics is changed by the nanoparticles, and that is responsible for the difference what we get in time of evaporation or the pattern of the motion of the Leidenfrost droplet between a pure liquid and a nanofluid. Because in the second case, when there is only deposition of those nanoparticles on the surface and we have poured pure water, we also find the similar kind of phenomena. So, now we go to reweighting of vertical tube. Now, reweighting of vertical tube, actually though people very loosely take, all the phenomena as film boiling phenomena, and many time you will find, probably we have also shown some time, that this is your pool boiling curve. Well, this is your pool boiling curve, and in many books etcetera, or conventionally people show that this is the Leidenfrost point, minimum film boiling point. But exactly the film boiling phenomena which occurs in different kind of situations are different. What could be the different situation? One situation we have seen that limited amount of liquid is there over a surface. This could be one kind of a situation. Let us say this is a very hot tube and you are supplying liquid through the bottom and it has to reweight and the surface has to be reweighted, but a liquid tongue will be produced. So, this is another kind of a phenomena. Or let us say you have got a tube, but you are injecting liquid. So, here also reweighting will take place, but this is again a next, I mean a different kind of phenomena. Or let us say you have got bulk of the liquid, your surface is very hot and here your vapor patch is being formed. So, this is another kind of a phenomenon. So, all the phenomena, if we try that there are similarities, but if we try to analyze them with the same kind of logic, there will be I mean we will not be successful. So, now I try to look into the reweighting of vertical tube. So, let us see how what is the issues here. So, here you can see this is just a photograph and then there is some sort of illustration based on the photograph. So, here we are passing the liquid and as the liquid passes through the tube, at one point the temperature is very high, it will not be able to wet the tube. So, the liquid will form some sort of a jet where it is not touching the wall and pass through the core. Now, this kind of liquid jet, they are very unstable, obviously they are not supported and they are flowing against gravity. A liquid jet falling from the top that could be quite stable, but this is going in the upward direction defying the gravity. So, this could be quite unstable and different kind of flow regime we can find out, which has been shown here. Okay. So, we can see the wetting zone, partial wetting zone, annular film boiling with surface waves, dispersed flow, etc., etc. And the obviously you can see the modeling of this phenomena could be quite difficult, but this is very important because in many of the engineering system, let us say that a pipeline is there which is to be filled up with LNG liquefied natural gas. So, initially this kind of phenomena may take place, or a cryogenic propulsion system of a spacecraft where the pipeline is to be filled up by cryogen. So, there also this kind of phenomena will take place, and more importantly in nuclear reactor, as I have told, this kind of phenomena will take place. So, we have made some study on this phenomena. Let us see what are the I have only shown you the interesting phenomena, not going much into the mathematics or much into the parametric study, etc., because I wanted to attract you to the beauty of the phenomena or to the intriguing nature of the phenomena. So, here also we have shown what is happening in case of a nuclear reactor. So, nuclear reactor, let us say some accident has taken place. So, after that the solid surface, whether it is a fuel bundle or so, its temperature will increase, and then there will be some sort of an oxidation, and then suppose from here we are putting the liquid. So, initially there will be film boiling, the rate of cooling will be very less for initial period, and then when nucleate boiling will take place, immediately there will be cooling, and very quickly it will come to room temperature. But during this period of time, when we have started our cooling, but we are not successful in cooling it effectively. So, many kind of catastrophic phenomena can occur, and this kind of material failure, rupture opening, fracture on coins, etc. So, those kind of phenomena can take place. So, this is only on the material side, but on the other side what can happen, as the surface is very hot and we have got vapor, etc., dissociation of the water vapor, that may also take place. So, if dissociation takes place, then there will be hydrogen generation, and hydrogen is a very explosive kind of this one. And in the later phase of Fukushima, if somebody has seen the U-tube, the entire dome moves up in the upward direction due to large explosion. So, many kind of catastrophic phenomena and particularly hydrogen generation, hydrogen explosion, that has taken place. So, after Fukushima, then not only on the cooling of the efficient cooling of reactor core, that has been one issue. This was an issue from the very beginning, but the mitigation of hydrogen, that is also another issue, though we will not discuss it in our lecture here. So, some history has been given that loss of coolant accident. Only when loss of coolant accident takes place, there could be different kind of accident in a nuclear reactor, but only when loss of coolant accident will take place, then the reactor core is getting heated up. Then the question of cooling it by some other means, which is called emergency cooling, that comes into picture, and then all the issues of rewetting, etc. So, all the important accidents what we know in the history of nuclear power, your 3 Mile Island accident, and then Chernobyl, and then last one Fukushima, which has time and again put some sort of a deterrent for the development of nuclear energy. So, we can see that there were loss of accident, a loss of coolant accident. Now, you see there will be host of other things, but along with that there will be loss of coolant accident also. So, this is some sort of a case study of Fukushima which has been given. It is taken from the net itself, and if you search this kind of phenomena you can get, and you can see the steam generation. So, steam generation at least visually one can see, but the oxygen generation and other kind of non condensable gas which will generate due to metal and liquid and metal and steam reaction, that we cannot see, which could be much more detrimental. Well, now let us come back to rewetting. So, rewetting, mainly there are two ways of rewetting as far as nuclear reactor cores are concerned. One is called top flooding. From the top you inject water, and you can get this kind of a phenomena. So, the water will come down, but it will not come down fully wetting the rod, because at one point due to vapor generation it will, I will show you photographs etc., or video etc. So, it will get separated from the wall, and wetting will not take place. In case of horizontal pipe, you can find this kind of a thing, because there will be stratification of vapor and liquid, and in case of vertical tube, the tube has to be totally flooded. So, there will be two front, one is some sort of a flooding front, which is the topmost part of the liquid jet, but it has not wetted the surface itself, and somewhere below we will have some sort of rewetting front. So, we will have both rewetting front and reflooding front. And obviously, in these cases hydrodynamic plays a role. As long as we have discussed this one, the leaden frost phenomena, hydrodynamics was not that important, but here the hydrodynamics plays a very important role. So, let us see. So, this is our experimental setup. Let us say this is a tube, and through this tube we have passed the water, and outside we have got thermocouple. So, from the thermocouple how the temperature is changing due to the passage of water, that we can find out, and the other components that has been shown here. Now, the convenient way of having this rewetting phenomena is to have a tube, heat the tube, and then quench the tube by passing water through the bottom. But if you do so, what is happening inside you do not know. All the phenomena which I have shown, that probably some sort of imagination, artist's imagination, that those kind of different flow regimes are taking place inside, but that you cannot see when you are using a metallic tube. So, what people have done, actually Harwell was very famous for research in nuclear engineering, of course, that is not there now. So, they had one method, and that method has been adopted by many people, at least some people, that neutron beam. If you pass neutron beam, metal wall is transparent to neutron beam, but water, I mean neutron beam for water, for neutron beam water is opaque. So, you can take a photograph. So, you should have a small reactor, you should have neutron beam produced, and then pass it through this, and then you can know that what is happening inside the tube. So, obviously, we cannot afford those kind of things for visualization. For visualization, we have made a very small, I mean very simple kind of setup, something in Indian terminology which can be called a jugaad. So, with that we have tried to do this. You can find this thing over here. So, we have made a tube furnace. Tube furnace means a furnace through which a tube can pass. So, we have made a tube furnace and we have used a quartz tube. So, the tube furnace heated the quartz tube in the dry condition, then by some sort of rope and pulley mechanism we take the tube furnace at the top, but the dry hot red hot, almost red hot quartz tube is there. Now, you quench it and you can see the phenomena. So, let us see, this is the this is how we have done it. I think nothing is there. Let us go to the next slide, then we can see some of the phenomena, I believe. And we will see those videos. But if we compare, then inside a metallic tube this kind of phenomena will happen, you can imagine, and inside the glass tube you can find this kind of a phenomena. So, metallic tube is having thermocouple. So, one thermocouple will give you this kind of a cooling curve. I think here I like to again go back to my write ups. You see, this is the pool boiling curve, Q delta T, and all of you are familiar with Q delta T curve, and you know this is the transition boiling, this is your nucleate boiling, transition boiling and film boiling. And you know that transition boiling is very difficult to get unless you have got temperature controlled system. So, you cannot get transition boiling. Now, quenching or reweighting is a phenomena where you get temperature control. You are not actively doing the temperature control, but you get temperature control, because let us say from 700 degree or 800 degree Celsius you are coming to room temperature, let us say 30 degree, 40 degree, without missing a single temperature in between. So, at each and every point what is happening you know. So, that means the entire boiling curve that can be traced using quenching phenomena. Of course, people may argue that it may have some difference with pool boiling curve, because there is a transient involved, and in case of reweighting there is some sort of motion of fluid is involved. But even then you can get a good idea how the boiling curve will look. You can construct your own boiling curve using a quenching experiment. So, the cooling curve which I have shown, temperature time curve. So, from there we can construct boiling curve also, which I will show later on. So, let us so temperature reading I have shown. Here what we have done, we have also used an infrared camera, and as the quenching front progressing in the upward direction, you can see how the temperature is changing. So, from the bottom it is getting cooled going in the upward direction, and you can see from the infrared camera also you will get an idea of the cooling of the rod of the tube, and that matches very well with your thermocouple data. So, that is what has been shown here. These are different parametric variation with nanofluid also we have seen the quenching phenomena or reweighting phenomena, with water also we have seen the reweighting phenomena. But well, these, as your common sense says, the same way the phenomena will proceed, that with flow velocity the quenching will be faster, nanoparticle concentration is increasing, your quenching will be faster. So, all these things you will get, there is no element of surprise, these are more or less follows the physics, and we can get some sort of data out of this, and probably we have got also quench front velocities etcetera from there. There will be lot of scatter, but one can find out reweighting velocity or quench front velocity. Coins front velocity depends on factors like initial wall temperature of the tube, coolant injection rate, concentration of the dispersed nanoparticles in the nanofluids. So, all these things you can find out, which are not very counterintuitive. This all comes from your common sense. But then what we have done, we have given for nanofluid there is no correlation. So, we have given some sort of a correlation, that is also not great. With little bit careful experiment you can get some sort of a correlation, and with pure water whatever was there. So, that correlation can be modified. So, that we have done. Correlation matches well with our experimental result. So, I think I will skip this thing, but these are important things. You see how the quenching takes place inside a tube. Visualization is very important, and we have taken different flow rates. So, with flow rate how it is changing, so that you can find out. Now, at the right hand side, one is water and one is nanofluid, but nanofluid concentration has been kept very low, otherwise you cannot visualize. But even then you can see the in case of nanofluid, let me run it once again. So, in case of nanofluid, the sorry. Oh, it is very difficult. Okay. But in case of nanofluid, the this thing is very fast, the quenching is fast. And inside what kind of phenomena, multiphase flow phenomena you can you can see what a complex kind of phenomena takes place inside the tube. So, again some sort of visualization has been shown, and how with flow rate it is changing, those things has been discussed. So, as we have lost some time, I will rush through, but these are I think important or interesting thing you can see. So, how really quenching inside takes place. This is another interesting slide. See, I think this slide you have sorry, this photograph you have seen. So, this is important. After that I will tell you something. So, Professor Banerjee was talking about this thing, instabilities. So, probably Kelvin-Helmholtz instability and Rayleigh-Taylor instability, those have been told. Actually, Taylor he has told regarding different kind of instability. Another kind of instability one can see, suppose there is a liquid jet falling in the downward direction. So, one can get this kind of instability, Rayleigh plateau type of instability, and then it will break into droplets. So, here we are having a reverse jet. In the second figure from the left hand side you can see a reverse jet and very beautiful Rayleigh plateau kind of instability and breaking into droplet that you can find. Okay. So, as I have told that as in multiphase flow there are interfaces, you can get different kind of instabilities related to the interface, and this is showing one unique instability in multiphase flow. Now, I have told that okay, sorry. Now, I have told that we have to we can determine the boiling curve, and for boiling curve actually you need two things. You need heat flux and you need temperature. Temperature you are directly measuring from thermocouple. So, time temperature history, from there you can get temperature, but heat flux you are not measuring. So, heat flux how we can get? We can get by some sort of inverse technique. That means, by the temperature measurement and by the from the time temperature curve using number of thermocouple, making some sort of a energy balance, we can get the heat flux. So, this is showing, this is a very standard technique, this is nothing new, we have not done anything new. So, with that you can find out what is the wall heat flux. You have to take a small control volume, and for the time history of the temperature whatever you get from the small control volume, making an energy balance, you can get the heat flux. And you see here there are two heat fluxes, just a minute, QR and QC. QC is the convective heat transfer coefficient or convective heat flux, this is the radiative heat flux, and you see dt, that means time time derivative of temperature, this is the double derivative of temperature. If this thing you can find out from the measurement, then most of the things in this equation is known, and then you can find out what is the heat flux. So, once you get the heat flux and you get the temperature, then you can get the boiling curve. So, that is what is done. You see QC ultimately we can get in terms of all these things, most of these things will be measured and obtained from the time temperature history, and then you can get a boiling curve like this. So, we have shown it in the 3 coordinates or 3 planes. This is the original time temperature curve, this is the boiling curve, and this is how heat flux will vary with time. And you see where there is a nucleate boiling, in this region heat flux is quite high. Before that there will be film boiling region, so heat flux is low, and in the forced convection also heat flux is low. So, this kind of a boiling curve you will get, and you see it is more or less I mean having good amount of concurrence with your pool boiling curve, and transition boiling region you can get. Okay, at least you can get some transition boiling region. Transition boiling is a very dicey region. I need not I do not want to say that this represent the transition boiling in all the cases. There are many controversies regarding transition boiling. People say that there are 2 transition boiling curve, people say that there are infinite number of transition boiling curve, but at least which is very difficult to measure. So, you have some idea how the transition boiling curve looks from the quenching experiment or from the rewetting experiment. So, this is how you will get the boiling curve, and you see here the critical heat flux that goes on increasing. Okay. Obviously, we have got different kind of nanofluid. So, with the nanofluid we are able to raise the critical heat flux. So, this is also one information which is important, that boiling heat transfer. In the next session or next lecture I will cover some aspects of augmentation of boiling heat transfer, but here we are getting a clue that with nanofluid people have shown it. It is not that we are the first person to tell, but this is experimental result what we can find that it is increasing. Different CHF values we have plotted, parametric variation, and so this is the parametric variation what you can get. That maximum heat flux, it depends on type of nanofluid, concentration of nanoparticles, coolant injection rate, initial wall temperature, location of the tube. So, with all these things we can get the change in maximum heat flux. So, many things are not very clear, like why initial wall temperature will give a higher CHF value. This has been reported even in my PhD, my own PhD. I have done some work related to this. There also I have found it, but so far no clear explanation has come that why initial temperature will increase the critical heat flux, or it depends on the location of the quench front. Near the bottom we will have some value of critical heat flux, near the top we will have some value of critical heat flux. So, I mean these things are not very clear, and theory, the type of flow phenomena I have shown, that anybody will admit that making a very good theory that is difficult, taking into the flow phenomena into consideration. So, that has also not been tried, but these are more or less trend which has been found by other people also. After the experiment, we have cut the tube. So, we can see depositions are different in different part of the tube. In bottom part there is larger deposition, obviously it remains in connection with the nanofluid for a larger period of time. Top section we have got a lesser amount of deposition, and then what one can say, probably that is one reason why there is a variation of CHF. But the fact is, even with pure water also, if we do the experiment, the CHF depends on the location of the tube. So, this is not very clear why it has happened like this. Some amount of metallographic studies we have done nowadays, these are all available. So, with that, if you do, you can see how different material has been deposited at different places. So, here also you can microstructure, you can see that deposition of nanoparticle forms a porous structure which helps in faster heat transfer during rewetting in comparison to water, and increases the surface roughness also, micro roughness I should say. Formation of micro cavities are responsible for increased wettability of the surface. So, these phenomena are there. So, to some extent it is not counterintuitive that, well, nanofluid will increase the effectiveness of rewetting, or it will decrease the rewetting time. Only what is important, it is not the bulk property, but what the nanofluid does to the surface, that is important, at least for this particular case. May not be in other cases of heat transfer, but for this case of boiling phenomena it is important. Some conclusions we have given here. Most of the conclusion are intuitive, not non-intuitive, but obviously the richness of the phenomena and richness of the flow regimes which we can find out inside the tube, that is really unparalleled, and it poses some sort of a challenge to the theoretician to make some sort of a formula or modeling which can be done for the quenching with nanofluid. Now, I will go very quickly to top flooding, very quickly whatever we have done. 11 o'clock we have got a break or what? Okay, we will take some time, maybe the next lecture we will, I have got less material to cover in the next lecture, at least I have brought less material. So, you will see. So, you see this is the experimental setup. Let me explain the experimental setup. So, you see this is again a heated tube, but here the outside of the tube is being quenched. So, what we have done here, we have made some sort of water injector, which I will show a photograph, and from the water injector there are some extended parts, so that on the tube wall it forms a small film. Of course, jet injection is possible, many people have done, but we wanted to have some sort of a control, and we wanted to have some sort of uniformity on the periphery of the tube as far as water distribution is concerned. So, we have gone for this kind of a experimental arrangement. So, this is what has been shown. Some of the parts probably we can see, and the tube inside there was heater, and with that we have heated it, and if there is injection through a nozzle, then what happens, there is maldistribution of water, and due to maldistribution of water there is bowing of tube, that also one can find out. Of course, one can think of multiple jet, but we have thought of a peripheral kind of a fluid injection system. At least initially the fluid injection will be uniform, though that also does not prevent the bowing of the or non-uniform distribution of the film as it falls down. So, this is what I have told that we have used a fluid injector. So, from different parts the fluid is coming and then the fluid entering the injector and or distributor, and from here the fluid is coming on the wall of the tube. All right. This is how you will find the reweighting. Okay. Uniform liquid film as long as it is weighted from the top, but as it come in the hot zone where the wall cannot support the liquid film, direct contact with the liquid film. So, you can see this kind of sputtering or deviation of the liquid film from the wall. So, that is you can find. So, you see the reweighting phenomena in bottom flooding, which we have seen earlier, and in top flooding they are different. Can you see that you will be bending or swaying, not bending, it is swaying, because let me see, because most of the liquid is not. Okay, with single liquid, a single rod we can see this thing, but definitely this is not there in nuclear reactor. We will in nuclear reactor, particularly HWR, advanced heavy water reactor, which DRC is have designed, and they will depend one of their main reactor like this. We have got so many tubes. So, this small circular this thing, this is called a spacer for the tube bundle. So, in the tube bundle there will be so many tubes, and inside there will be a large tube, large diameter tube, and in this large diameter tube axially at different point there will be holes. Through those holes liquid will be injected. Just for visualization, what happens in case of a single tube, because so many tube will be there, what is happening to a single tube you will not know. So, that is why we have done the single tube experiment, but in actual case this will be the configuration. And 59 rod I believe. So, 59 sometime back we have done this experiment. So, 59 rods probably will be there and very closely spaced. We have done almost a full scale experiment, 3.5 meter height of these each of these rods, and at regular interval these spacers are there. Otherwise, I mean the rod you can see that they can sway so much. So, one rod will touch another, there will not be liquid distribution, proper liquid distribution. So, there will be spacer plates, and we get this kind of quenching curve. I will here what we have done is basically color liquid and air, because there will be steam will be moving up. Liquid from the top is being injected, it is coming in the downward direction. So, if there is lot of steam generation, then the steam will try to eject the liquid from the bottom to the top. So, cooling will not be proper, and this is called counter current flow, and there is something called counter current flow limit, CCFL. So, that is very important to determine. If the entire liquid is taken up, then you cannot cool it. Emergency cooling system you have to design. So, you have to ensure that all the rods are getting the coolant and steam is not taking it outside. So, these are the some of the phenomena I have shown, I will not explain it, but interesting to see. Some conclusion I have made that if there is air flow, then quenching will be delayed, there will be different quench front. Once it will quench, come up to certain level, then it will not quench, again a new quench front will start. All these things you will find with the injection of air from the bottom. but this is how is the AHWR rod bundle. We can see that 3 rows of rods and they are very closely spaced inside. So, this is our experimental setup, and this is how is the central tube and the peripheral spacer for the peripheral tubes. This is how in the central tube we have got number of holes at different locations. So, these are the holes through which water is injected. Water comes from top to bottom. This is in between the fabrication process. Fabrication is also very difficult. So, these are all electrically heated rods and lot of thermocouples are there, and again it has to be held at top and bottom. In between spacers are there, spacers are not fixing them, but guiding them. So, there could be end plates like this. Through these small holes each of the heater will be held. These are some in between fabrication process. So, lot of thermocouples, numbering of thermocouples, all these things will go on. So, you can see almost 100 kilowatt of power we have used, very downscaled, but even then it was a big job for us in the teaching institution. So, these are different kind of things. So, here you can see probably that one has to see whether the lowest or the outermost periphery is also getting wet or not. So, we have done some is there any movie? No. So, we have done some test and see that in the glass tube also the water is collecting. So, that up to outer periphery the water is coming.
देख लो आप सीढ़ी लगा के।
Nothing much we can see, but this is the test matrix. This is the test matrix. These are the kind of diagram we will get. Suppose we have taken a particular rod and at different location thermocouple we have fixed, and from the different thermocouple we have got the time temperature history or time curve. See, for BRC it was important to know whether all the rods are getting quenched, all the parts of the rods, that means it is 3.5 meter long. So, top is also getting quenched, middle is also getting quenched, bottom is also getting quenched. So, what we can see more or less within a small period of time all the our setup was such that we could test the proposition. But what happens sometimes in between there are fluctuations, like one quench curve starts, for some time again there is no cooling, and then there are cooling again. That means, the water supply is not continuous for all the rods. So, there is some intermittency. Of course, that intermittency ultimately does not affect the cooling. So, that is what we are getting. More than that, visualization is not possible in these cases. Here also you can see that initially there is cooling, it is generating heat. So, in between there is no cooling. So, temperature is again shooting up, but ultimately it is getting cooled up, cooled down to the room temperature. I think I will show here. At the top we have got some venting, and you see vapor is coming in the upward direction. We can see it. Vapor also takes certain amount of liquid, parts of liquid comes out. More than that, it is, at least in our setup, it was not possible to visualize what is happening inside. So, this is what we could see, and I mean, this is the first full scale, they call it in bundle coolant injection. Globally, this is the first full scale in bundle coolant injection testing, and more or less the design was good. The way they have done and the way we have told them to put the pressure of the supply liquid and the hole diameter, the frequency of holes. So, more or less that is sufficient to get the cooling. So, coolant reaches the entire length of the rods at all flow rates irrespective of the position of the thermocouple with respect to the ring sector. In spite of parametric variation over a range, cooling curves show similarity in their trends. So, though there are fluctuation, so it shows similarity. As soon as coolant reaches the rod, instantaneous cooling takes place up to a temperature around 100 degree Celsius. After that, cooling is slow, because beyond 100 degree Celsius it is then convection, no boiling takes place. In the second phase of cooling, often lot of fluctuation appears. 100 degree to room temperature, lot of fluctuation appears. Vapor plus liquid mixture comes out of the steam exhaust. That means, this counter current flow is there. It is not it has to be, steam has to escape, but when the steam escapes, it will also take certain amount of coolant along with it. Some fluctuation in the temperature occur due to the counter current flow. So, this is another thing. This is the that time these are the students. Subramaniam is also here. Subramaniam, can you identify yourself? Subramaniam is here. Two persons have done most of the work. The first work which I have shown, bottom flooding and rewetting, that was done by Gayatri, who is now a PDF in CMERI, I believe, or some project, and another was MS student, the later part of the work. After MS he left, but now he is in, I think, Canada or Australia somewhere doing his postdoc after PhD from IIT Bombay. So, I am grateful to all the students. Actually, not only these students, this was such a big program. So, many people from the laboratory also helped them. So, my gratitude to all of them, and if there is any question, I will be happy to answer. Particle chemistry we have got, actually most of the results here has been shown by TiO2, but TiO2 nanofluid, but we have done also Al2O3. Al2O3 is also very common nanofluid. Now, in all the cases one can find those from the characterization after the quenching, one can find those particles. But surface structure is changed to a very great extent. I do not think there was any chemical change, but deposition was not uniform, as it cannot be, and there were some sort of a spongy layer, there were some roughness created, some holes created. So, all those things were there. So, roughness and those structures I think are responsible for higher rate of heat transfer, and not higher rate of heat transfer, but from transition from film boiling side to the nucleate boiling side. So, always we know that when there is a roughness of the surface, the boiling heat transfer increases, and it has got a say for the transition from film boiling to your nucleate boiling or transition boiling. So, that is what has happened here. Jangho Kim was Maryland was the examiner of Gayatri's thesis, the first part of the work. Maybe. Depositing the particles itself. That. Same level of this thing. So, we are supporting, or we think also in the same way. We also think in the same way. No, actually, let me tell you, that is what I am time and again I was giving a rider, that nanofluids are used in many places. So, in many cases it is for pure convection, single phase convection. That part I am not debating, though I have got some opinion regarding that, that part I am not debating. As far as boiling is concerned, if we see the boiling heat transfer is dependent on properties, obviously it depends on thermal conductivity etcetera, but it is more dependent on how nucleation is taking place. So, here the nanoparticles or nanofluid has got a slightly different role. Okay. So, boiling and single phase if we compare, then it would not be proper. So, here the nanoparticle has got a different role, and in some boiling experiment people have seen the boiling heat transfer to go down. There also people have given one logic that maybe some of the crevices etcetera, those are plugged or evened out by the deposition of nanoparticles. So, that kind of logic has also been given. Problem is the trend of result which I have shown for quenching, for reweighting, this kind of trend, because MIT is also interested in using nanofluid in this one. So, there are different groups. Similar kind of trends have been obtained, but a thorough pool boiling experiment starting from the inception of boiling till film boiling region, nobody has done very carefully, nobody has done cared to see what is happening. See, nowadays it is not very difficult, only problem is the nanoparticle concentration, if it increases, then visualization becomes difficult. That is of course one difficulty, but that has not been tried. So, that is one part one needs to do.
So, that means that the duration for which the experiment is performed.
Repeatability of the experiment, more intermediate results. See, suppose we do experiment for some time, then we take microstructure, those kind of things, visualization, if possible bubble release pattern. So, all these kind of things are to be seen. Full boiling curve has to be what should we say, reproduced repeatably for number of times. So, those things are to be done, if at all people are interested in nanofluid kind of a thing.
So, what I was implying was the same experiment done for 2 hours versus the same experiment done for 4 hours might end up giving you 2 different.
I will show in the next lecture that boiling augmentation, same surface used for initially brand new surface and 2 hours, 8 hours. So, aging is there, aging is there.
So, there is a fine balance between creating nucleation spots and fouling.
Yeah, that is true, that is true. Actually, in boiling, I think who has told it? Somebody told it that there are many nuisance variables. So, those nuisance variables, many cases we are ignorant, we are unable to get rid of those nuisance variable etcetera. So, that has got lot of thing to do with boiling. Any question from the students?
So, you told that if we increase the concentration of nanoparticles, then it will be problem of visualization. Is it the only problem for which?
No, that photograph which I have shown, that is actually you see this has been seen in case of nanofluid also. In we are familiar with one thing which is called law of diminishing return. Water to let us say some x concentration of nanoparticle, you will get some augmentation. 2x, the augmentation rate will not be the same. 3x, the augmentation rate will be lower, and then more concentration means more tendency for sedimentation, aggregate formation, clogging, etc. So, there are other problems, but here I have shown it because we have to visualize it. So, that is why I have shown it with, or we have done the experiment with various dilute nano fluid. Okay. So, if there is no other question, then we can take a break. Somebody was asking that really what is happening regarding, I mean during reweighting. As I have told, reweighting is, or the phenomenon of film boiling to coming back to the nucleate or transition boiling for that matter, is different for different situation. So, let us see what is happening in case of a tube when there is bottom flooding. Bottom flooding means liquid is coming from the bottom. So, here some nucleate boiling is taking place, and after that this is the liquid and this is vapor. So, you see this surface is very hot, this surface is very hot, and but as lot of vapor is passing. So, this surface is getting cooled, and then this reweighting front can move up and up. So, this is what is happening in case of bottom flooding. In case of top flooding, let us say this is the surface or the tube, you are injecting liquid. So, liquid is falling because the surface is cold, and after that liquid goes away from the surface. So, here how the reweighting is taking place. For reweighting, what you need to do or what you need to have, that the surface has to come to a lower temperature where it can sustain or support intimate contact with liquid. So, here what is happening, up to this it is cooled, let us say this temperature is 550 degree Celsius, and here it is 500 degree Celsius. So, you can see that there is a very large temperature gradient along the axial direction. So, obviously, there will be lot of heat transfer from this side to this, and then at one point of time it will come to let us say 120 degree Celsius or so, and then your cooling by liquid will be possible. So, in the second case it is called conduction controlled reweighting. So, when there is top flooding, so it is called conduction controlled reweighting. We have also some model on conduction controlled reweighting. Those thing theory I have not discussed. I have purposefully not touched theory. So, in the second case this is how the reweighting is taking place. Well, so with this let us go to the second topic. Augmentation of heat transfer in boiling and condensation. Now, what has happened that with the growing interest of nanotechnology, micro scale devices, micro fabrication, and measuring instruments which can probe into smaller scale, the augmentation of heat transfer in boiling and condensation has taken a new shape. So, there are really very interesting issues and there are intriguing situation, there are very intelligent solutions, but those things I will not cover in this lecture. Rather, I will like to concentrate on I mean the aspects of augmentation of heat transfer which are for large engineering systems. This thing we have to understand that let us say on a chip level what augmentation technique we can adopt, the same thing we cannot adopt for some sort of a boiler tube which is quite a few meter long, whose diameter is of the order of 1 inch or half an inch. So, there we cannot adopt the technique which are adopting in case of a silicon chip. So, I will rather try to concentrate on those engineering thing but some aspects we will time to time we cannot make that kind of a demarcation. So, we will when it will come we will discuss some aspects of that. Now, augmentation of heat transfer means increasing heat transfer, rate of heat transfer, and we know there are three modes of heat transfer: conduction, convection and radiation. So, one can argue that well, we can also increase conduction, we can also increase radiation. Like conduction can be increased, let us say there are two metallic surfaces in between, I put a thermal paste. So, that increases the conduction heat transfer. Like for radiation I can give a surface treatment or surface design I can make such that my radiation heat transfer there is an improvement, but generally these are not discussed under the purview of heat transfer enhancement or augmentation of heat transfer. Augmentation of heat transfer, the connotation is that we try to improve the convective heat transfer. I mean the methods, techniques, physics, art, whatever it may be related to increase of convective heat transfer. Now, convective heat transfer, the formula we know, Q is equal to H A delta T. So, either we use H or we use A, sorry, either we increase H or we increase A, or many of the cases we increase both H and A. So, this is what we try to do in heat transfer augmentation. Applications are many. All the application I have given classical application, power and cooling application, renewable and non-conventional energy, electronic component, automobile, space, marine, etc., fuel cell, reactor, process plants, and lastly I have given the new applications like MEMS, biological, medical applications, microfluidics, etc. So, which probably I will not have time to discuss, and I mean purposefully I have kept that, because those principles are very new. I do not know Professor Banerjee whether he will cover some of these or not, but in my lecture mostly the conventional thing on metallic surface, how the augmentation can be done. So, those are metallic components. So, those things have been discussed. So, augmentation of heat transfer, pros and cons, if we see that obviously, if we have high heat transfer, then my equipment size and ultimately the plant size will be small, weight will be small, footprint will be small. So, that is good, and at the same time for mobile system that is also very good, because the weight means the tractive power, it is proportional to tractive power. So, tractive power will also be less. Higher rate of heat transfer, good for energy conservation. Suppose I am generating fossil energy from the fossil fuel. So, if I efficiently can transfer energy, for which thermal energy is one of the prime mode. So, obviously, I am going towards energy conservation, and less loss, good from environmental point of view. Any loss is a potential pollutant, whether it is heat, whether it is water, whether it is something else. So, if we reduce the loss, then pollution I am cutting and degradation of environment I am preventing. Then can reduce both initial and running cost. Running cost definitely it reduces. Sometimes if I have got small and compact plant, then it also reduces the initial cost. Cons, most of the cases we have higher pressure drop, higher initial cost, because I have to have some unique design, and high maintenance, in many cases I have to have high maintenance. So, these are the cons of our augmentation of heat transfer. What I will do though well, so augmentation of heat transfer, first I just like to give a small overview of what we do in case of single phase convection, because you see convection is the main thing or the underlying mechanism even for boiling and condensation, and some of the single phase techniques are also used either in the direct form or in the revised form, modified form in boiling and condensation. So, I will give an overview of that very quickly. So, active augmentation technique. Active means I need some power for it, some auxiliary power is needed. some power source specifically needed for augmentation. So, fluid pulsation, suppose I want to give some sort of a pulsating motion to the fluid. So, sometimes I have to use some power device for that. Surface vibration, so suppose heat transfer surface I want to give some sort of a vibration. So, that needs power. Mechanical agitation, let us say with some sort of a mechanical circulator, turbulator, so power is needed. EHD, electrohydrodynamic method, so that also needs some sort of power. And body force field. So, body force field, sometimes we need a body force field artificially created for higher rate of heat transfer. One example could be in space application, where we do not have gravity, we might have to create some sort of a body force field to have, or at least people have proposed that that could augment the rate of heat transfer. Passive technique which does not need auxiliary power. It may need more power due to pressure drop, higher pressure drop, but it does not need specifically an auxiliary power source. Fins is probably the most versatile method of augmenting heat transfer. Then surface modification, it has got enormous potential for augmentation of heat transfer. Swirls, that we make the design such that the fluid is getting some sort of a rotary motion over and above its axial motion. Then insert, different kind of inserts can be there, means original tube is there, apart from that we are having some mechanical component which are called inserts. Then additive to the fluid, with the fluid we can have solid particle, with the fluid particularly with the liquid we can have some other liquid to enhance the rate of heat transfer. So, these are, I do not claim this is all inclusive, but these are some of the techniques which are generally used. So, let us say quickly, very quickly we see how in single phase flow heat transfer augmentation can be done. So, on the left hand side we can see some example. Let us say this is a this could have been a normal tube with constant diameter, but here we have created this kind of protrusions, so that the fluid has to go like this. So, 2-3 different things will happen. First, what will happen? It is increasing the fluid path. So, there will be more residence time of the fluid, more time the fluid will be in touch with the solid surface, and then it will break the boundary layer. Boundary layer will grow from here, let us say, or from here there will be a small break here, after that there will be a break here, and after that again there will be a break here. So, when the boundary layer is broken and new boundary layer is formed, the thickness, it has to start with 0 thickness or small thickness. So, heat transfer coefficient will be large, and then it gives some sort of a mixing of the fluid. You can see that there will be some sort of a mixing of the fluid. The second one is also like that. In this case, suppose I have got this much of length available, instead of putting a straight tube I have put a spiral tube. So, the spiral tube will give me a higher residence time. At the same time, though the main flow in this direction, but the fluid has to take a path like this, there will be a secondary flow and heat transfer coefficient will increase. So, single phase flow, these are very common example, even some of them can be adopted in multi-phase flow. Some other example, let us see. This is a twisted tape insert. I have told regarding twisted tape insert. So, you see inside the tube there is a twisted tape like this, and it should not, means it need not touch, the wall. So, the fluid has to take then this kind of a path, the fluid mixing will be there, and due to mixing there will be a good amount of heat transfer. Okay. And obviously, one can assume, though it is used both in laminar and turbulent flow, that in laminar flow the effect will be much dramatic compared to turbulent flow. And then there are different variation of this twisted tip. Somebody may argue that you see, for case of turbulent flow the mixing in the core is very good. So, why do we need this twisted tape at the middle portion? So, we can have this kind of a narrow tape like this, and that is how I will reduce the pressure drop, but I will have a good heat transfer. Or somebody may argue that, well, at the wall heat transfer is taking place, let us agitate the fluid at the wall itself. So, we can have some sort of wire insert which is near the wall rather than having it in the entire bulk of the fluid. So, these are some of the method which can be used. These are some sort of fluted tube, and you can see that there are spiral flute inside the tube. If you closely look into this, so there are surface parameters in the inside of the tube, and these surface parameters, these are very small, they are not fins, but they will perturb the boundary layer, and at the wall they will give some sort of a different direction of motion of the fluid. So, with all these things we can have a higher rate of heat transfer. Okay. Some of these can be used in two phase flow also. Fins, as I have told, it is very versatile device for heat transfer, particularly for gas side heat transfer. Fin is one of the methods most commonly used. These fins are taken from fin tube heat exchangers, and in fin tube heat exchanger different kind of fins, rectangular fin, offset strip fin, triangular, etc. one can see. And when we are having these fins, and particularly this kind of variation, this is a longitudinal fin, rectangular fin, but when we are having this kind of variation, we have got lot of advantages. So, as I have told, fin will increase the heat transfer area, but when we are having this kind of variation in the fin geometry, it will also enhance the H. That means, we will have both increase in A and H. So, heat transfer coefficient, rather rate of heat transfer will increase. Let us say in a plate fin heat exchanger, we are having small kind of features like this. These are called delta wings. Of course, all of them are not delta. Air is flowing like this. So, fin will increase the increase the rate of heat transfer. At the same time, the air flow, due to the presence of these elements, it will create vortex behind these elements. So, that will create increase the local heat transfer. So, we are having a second generation of augmentation in heat transfer. First, we are having with the help of fin, then we are having it with the features provided on the fins. So, many augmentation technique we will see, there are hybrid technique where 2-3 different techniques are mixed together. We will have more generation of augmentation techniques coupled together to have a higher rate of heat transfer, and this is becoming more and more important, because we want to have more heat transfer within a small volume. For a small delta T, we need to have a very large heat transfer. We need to provide in many cases an isothermal surface, so that from everywhere a good amount of heat is being taken. That means, if we have this flat plate, so here the heat transfer rate will be high, and as the boundary layer grows, the heat transfer rate will be low. So, we cannot afford it in many applications. So, we have to have some sort of uniform or rather isothermal condition of the surface. In fact, I do not want to elaborate on those things. You see the next level of integration in case of electronic industry, that is so much dependent on thermal management, and augmentation of heat transfer is the call of the day. Now, augmentation of heat transfer in boiling and condensation, what are the challenges? Heat transfer coefficient in boiling and condensation is already high. See, it is a very common example, all of you either student or teachers, that somebody who has got 50 in some subject, it is not very difficult for him to try and make it 60 or 70 in that particular subject, but somebody has got 95 to make it 100 or 90 to 95, that is very difficult. So, already the rate of heat transfer is very high in boiling and condensation. Condensation, in some cases it gives the highest rate of heat transfer amongst all the examples. So, there to increase something that is quite challenging. Then as I have told that pressure drop is associated with the augmentation of convective heat transfer. In two phase flow the pressure drop is high. So, a higher pressure drop could be another challenge in case of our augmentation technique in boiling and condensation. Then additives may damage the surface. So, in some places people may put additive, as what I have told we were discussing, that nucleation sites may get damaged by, may get plugged, clogged, etc., by the addition of additives. Then there could be change of flow regime due to a particular type of flow regime. Flow regime means the particular configuration of the distribution of the two phases we want, but that may be changed due to the augmentation technique adopted. Now, one can have it for advantage, one can get some disadvantage out of it, means I can model the flow regime according to my wish. I will give some example. So, that is one thing we have to keep it in mind. So, with these constraints we have to go for heat transfer augmentation in boiling and condensation. I will discuss most of the thing in terms of boiling. Condensation, some of the things are common and some new things also I will discuss over there. Now, if we have to understand the boiling augmentation of heat transfer in boiling, though in many cases we will be concerned with the flow boiling, but let us first understand the pool boiling curve, because many features of the pool boiling phenomena will be present, and keeping those in mind we have to design what could be the augmentation technique for boiling. So, I think it is known to all of us that initially there is one natural convection, then there is one ONB, onset of nucleate boiling, then there will be nucleate boiling, but this nucleate boiling region initially there will be isolated bubble, shown isolated bubble, then jets and plugs etc., bubbles are merging together. So, fully developed nucleate boiling. Here we will have critical heat flux, beyond that we will have transition boiling. We will not go beyond that, because in most of the industrial application, if we like to use boiling for having good amount of heat transfer, then we operate in nucleate boiling region. So, we will not go beyond critical heat flux point. But one thing is important, that if we go for heating, then I will reach critical heat flux point. If I am going from coming from this side quenching, then probably I will reach this point, I will bypass the critical heat flux point. So, this we have to keep it in mind. Most of the cases we will follow this point. So, this part of the curve is important. So, next slide if we see, let us say this is on for a normal surface, this is the boiling curve, nucleate boiling curve. Here it is ONB, sorry, here it is ONB, that is onset of nucleate boiling, then this is the nucleate boiling, initially isolated bubble, then the bubble jet columns etc., and here it is the critical heat flux. So, this is what is given by a particular device. Now, I want to do some augmentation of heat transfer. So, I like to have a curve like this, for which the ONB will be shifted in the left hand side. Let me tell what are the issues. What is ONB? Water on a saucepan will not start boiling at 100 degree Celsius temperature of the saucepan wall. So, we need the saucepan wall to have some higher temperature, let us say 110 degree Celsius, then only it will start boiling. But we know that boiling will give you high rate of heat transfer. So, if the boiling start at let us say 2 degree Celsius of superheat, then that is good. So, we want the ONB to go in this direction, at a low temperature the boiling should start. We want the nucleate boiling portion, the heat transfer will be high. That means, for a given delta T, Q should be higher, and we want critical heat flux to move in this direction and move up. That means, up to a larger temperature, I should have safe nucleate boiling, and up to the maximum heat flux, that will be more as possible. So, these are my dream, that if I can have this thing, then I have got a good surface, let us say surface for boiling. So, boiling augmentation not boiling, that should be like this. Here I like to go back to some of the things which I will draw or tell. Now, please bear with me, because some of the fundamental things now I like to go. I think that would be important to know. Now, what is the process of phase change? So, phase change means from one phase we are getting another phase. Liquid, from liquid we are getting vapor phase, that is we are now discussing, or from liquid phase we are getting from vapor phase we are getting liquid phase. Now, how the phase change occurs? Have you ever thought, or have you ever read? A new phase is to be created. So, basically if we think, or if we consult physics, it is like this, that there are some sort of fluctuations of the molecules. The molecules will have different energy level. So, there are fluctuation, then let us say high energy molecules, they will make some sort of a cluster, a nucleus will form, then the nucleus depending on situation can grow or cannot grow. If it grows, then there is a growth phase, after that we will get a new phase, and then a phase transfer, phase change takes place. If we consider the change from liquid to vapor phase, there are two things, and let us have clear cut idea regarding that. One we know is boiling and another is evaporation. Can you tell me what is the difference between boiling and evaporation? Because gas liquid phase change, two things are there, or two different modes are there. Physically what is happening in case of boiling, and physically what is happening in case of evaporation. Though evaporation is not our topic of discussion, but at least we should have some idea and then we should proceed. So, is evaporation a heat transfer process? Yes, no, no. Then, well, evaporation is a, somebody told me, though very anything, no. So, somebody told me evaporation is mass transfer process. Obviously, so evaporation is basically a mass transfer process, when there is a concentration gradient, then there will be mass transfer. For that mass transfer, some amount of latent heat is needed. The process is very selfish, from anywhere possible it will take the latent heat. Okay. From anywhere possible it will take the latent heat. I can give an example. Let us say you soak a piece of cloth in ice cold liquid and then you hang it. From the very beginning there will be some evaporation, but how the evaporation is taking place? Because the water molecule there, they are very cold, but even then evaporation will take place, because the ice cold liquid soaked cloth is fully saturated with water, and the surrounding air, that is not having that much of water molecule. So, there will be migration of water molecules, and for that, from wherever it possible it will take the latent heat, whether from its own body, whether from the ambient air, whatever it may be. So, it will take the latent heat. So, that is not our discussion, but in the other case that energy is very important and it is energy driven. That means, there is a initially these fluctuations are there and high energy molecules are coming together to form a cluster, and then that cluster grows and the phase change take place. New phase is generated and phase change is taking place. So, the initiation we can think of that nucleation is the initiation of phase change. If the nucleation is the initiation of phase change, and there are two types of nucleation, we know that homogeneous nucleation is there and heterogeneous nucleation is there. Let us think of a homogeneous nucleus of homogeneous nucleation, and there is a vapor bubble form like this. So, the radius of curvature it is 2 by r, and the excess pressure inside this bubble, that is 2 sigma by r. Okay. So, for mechanical equilibrium this is needed, that inside pressure should be, if this is vapor, this is liquid. So, inside pressure should be 2 sigma by r. And then P by P sat, what is P and what is P sat? P is the inside pressure and P sat is the saturation temperature, saturation pressure corresponding to the temperature at the interface. So, P by P sat is equal to, we will have exponential of minus 2 sigma V m by r RT. So, let me tell you, sigma is surface tension, V is the specific volume, m is the molecular weight, r is the radius again, and capital R is the gas constant, temperature, T is the temperature in Kelvin of the interface. So, this kind of a formula we will get. Okay. So, there is a difference between saturation temperature and the temperature inside the vapor bubble, and inside there is a difference between the pressure inside the vapor bubble and the saturation temperature, saturation pressure at the interface, and that is given by this particular formula. So, two aspects are coming, one is mechanical equilibrium, for which inside pressure and outside pressure can be correlated with this term 2 sigma by r, and from thermodynamics something is coming where we have got this formula P by P sat is equal to this one. So, how they are related with other processes? It is like this. We know saturation temperature and saturation pressure, they are closely related. So, let us say this side is T sat and this side is P. So, let us say this is P 0 and this is P g. So, we can have let us consider a bubble. So, inside pressure is P g, outside pressure is P 0. So, P g is more than P 0. So, the temperature also we can see that there is a difference of temperature, delta T sat is coming. It could be both bubble and drop. The same kind of analysis can be applicable for both bubble and drop. For the plane surface, this is the pressure and saturation temperature curve, but there could be subcooling, there could be superheating, or depending on the curvature of the surface, depending on the curvature of the surface or interface, we can have different phenomenon like this, whatever I have shown in this diagram. So, this is very important to understand. Okay. Now, we are talking about homogeneous nucleation. So, homogeneous nucleation will take place due to fluctuation, and inside the bulk of the fluid a new phase, bulk of the liquid, let us say vapor is forming. So, a vapor will form. The relationships which I have given, we can follow these relationships, and for that the delta T sat that is needed is very high. Okay. Delta T sat that is needed, that will be very high, and that comes from a very complex relationship. Okay. Thermodynamics is involved, some amount of mechanics is also involved. So, that comes from a very complex relationship. One relationship has been given by Professor Leonhard. So, Leonhard was or he is Professor Banerjee, Leonhard is still alive, no?
He is in University of Houston, yes. I had lunch with him and Professor Dept in April.
Okay. So, Leonhard is the grand teacher of Professor Banerjee, Professor Dheer's supervisor, and we those fellows who did not have the opportunity to see or to have close interaction. I have also seen him, I have also interacted with him. So, but we have some desire to work on in the field of boiling. So, we find that he is some sort of a father or grandfather figure in at least in some field of boiling. Okay. So, Leonhard has given some sort of a relationship delta T sat by T c, T c means the critical temperature, that is equal to 0.905 minus T sat by T c plus 0.905 T sat by T c to the power 8, very complex relationship. So, it gives how much delta T sat is needed for homogeneous nucleation. A closed this thing is there, means approximate. Let us say this is the homogeneous nucleation temperature, this is 0.91 T c critical temperature. Whatever we do, if we do the calculation, it is very high. That means, at atmospheric pressure 216 Kelvin is needed for homogeneous nucleation, whereas when we boil water in our kitchen, we see that 10 degree K, that is good enough for having homogeneous having a nucleation. So, the reason is that we are having heterogeneous nucleation in the second case. All right. So, that is one thing, that we are having heterogeneous nucleation, and heterogeneous nucleation needs very less amount of delta T to produce vapor from liquid. So, this is one crux of the point. That means, we will try to promote cases or promote situations on our surface, so that it promotes heterogeneous nucleation or creates situation like heterogeneous nucleation, where we will be able to make this delta T small, and at a earlier temperature we will be able to create boiling. And if we follow this, then of course, during nucleate boiling also we will have higher rate of heat transfer. So, just from simple physics one can tell this thing. Now, the question is, what is heterogeneous nucleation? Heterogeneous nucleation, in a nutshell, if I like to tell, heterogeneous nucleation is nucleation on the surface, on some sort of a substrate, whereas homogeneous nucleation is in the bulk of the fluid, heterogeneous nucleation is on some sort of a substrate, solid substrate maybe. Okay. Now, in the solid substrate, by some measurement, by some observation, it has been seen that there are preferred site of nucleation, which are called nucleation sites, and from there nucleation takes place. When is the car coming? No, they can wait outside, but everything will get delayed. So, I think I will do some part of it and then stop, because again afternoon we have got, or should I rush through? I thought this part needs little bit of explanation. I do not know, maybe I have gone to teaching mode, not in GAN mode. Okay. So, up to 1 there is no problem. So, I can have then some sort of a logical conclusion of this one. So, what is heterogeneous nucleation? Heterogeneous nucleation, then on the wall or on the substrate there are preferred sites on which from which the vapor generation will take place. Vapor generation will not take place from each and everywhere of the surface, but at preferred site the vapor nucleation will take place. So, these are called nucleation sites. What are these nucleation sites? These nucleation sites are cavities. So, the nucleation sites are cavities. Let us say we have got some sort of a cavity. This is a very exaggerated view of the solid substrate which we are having, and all the surfaces will have this kind of cavities. It is very difficult to make perfectly smooth solid surface. So, in this cavity there will be some sort of liquid and vapor. Let us say the liquid, there is bulk of liquid, the bulk of liquid is trying to come inside the cavity, and inside the cavity there is vapor. So, there will be some sort of interface created. Now, from where the vapor will come, those things I am coming later on. Now, what one can have? One can have either this kind of an interface. So, if this kind of an interface is there, so you see this theta, this is the contact angle, this theta is less than theta is less than 90 degree, and if this is vapor, this is P g and this is P 0, the bulk fluid pressure, then P g is greater than P 0. So, here due to instability what will happen, the vapor phase will try to grow and there will be more evaporation. On the other hand, if we are having this kind of a figure, then this is your liquid and this is non-wetting case, P g is greater than 90 degree, we will have the reverse situation. So, when there is a liquid coming in and trying to fill this cavity, so we will have the previous situation and we will have a growth of vapor phase and we will have the vapor generation. So, sometimes actually there are different proponents or there were stalwarts of boiling. One stalwart is D.B.R. Canning in UK. So, what he says that heterogeneous nucleation, well, for heterogeneous nucleation, nucleate boiling is a misnomer, because nucleation is not taking place, there is some sort of a gas and the interface is such that from the interface evaporation is taking place. Now, why there will be some sort of a gas? This gas or vapor, it could be a gas, it could be a permanent gas which is already there in the crevices or these small holes, or it could be the gas dissolved in the liquid itself. When the liquid comes, they occupy this, and once they occupy this, from here vapor forms. So, once vapor formation is taking place, there could be a mixture of gas and vapor. So, this process of vapor generation, it will be almost continuous as long as we are supplying the heat. And you see, by proper designing of this kind of cavities, one can reduce the degree of superheat needed for the generation of vapor. And this kind of cavities are called single entrant cavity. One can have re-entrant or double entrant cavity, which can be something like this. Okay. So, in this kind of re-entrant or double entrant cavity, the degree of superheat needed is even lesser. I am not going into derivation, as we have to little bit go fast. So, we have we need lesser amount of degree of superheat. So, this gives us another view that if we have this kind of cavities, and particularly if these cavities are properly designed, then we can have boiling quickly at low temperature or at low degree of superheat, and we can sustain boiling, or we can have boiling from many places of the surface. So, this is what we can have. Anything else? Yes. Another thing. So, let us say from the cavity when boiling is taking place, how the boiling is taking place. So, probably it will be taking place like this, like this, like this, like this. So, you see ultimately there will be some sort of a neck formation, and then this vapor bubble will get detached from the surface, and then another bubble will form. But when the neck formation is there and this bubble is getting detached, some amount of vapor will be left in the cavity. So, that will be again used for the next phase of the evolution cycle. So, this is how continuously boiling will take place. That means bubble generation, then there is a small waiting period for the next bubble to come, and then another bubble generation. So, this is the cycle which we will have, and when there is a large surface, there are large number of nucleation cavities, etc. You can see that almost that continuous phenomenon of boiling is taking place. So, there are many things important, that liquid and surface compatibility and characteristics, cleanliness, surface apertures, etc. Then temperature and heat flux. So, all these things are important, I am not going into this. So, this is one thing which we can see, and re-entrant cavities are very important. Cavities and re-entrant cavities are very important. Now, these are not very great thing, we can see these things very well in our naked eye also. Let me tell you one thing. Suppose you have got a saucepan and just put a spoon or ladle while boiling, you will see lot of boiling is taking place from this part. So, because it is giving the opportunity of vapor formation, where you have got some sort of a conical structure formed by the spoon and the surface of the saucepan. Okay. So, to make some sort of time saving, let us go to the next slide. Here there is another curve very important from theoretical analysis. Where is that? One will get this is the cavity mouth radius by which the cavity is defined, and this is T w minus T sat, and you will get this kind of a curve from thermodynamic and mechanical analysis. This is the range of the active cavity size. So, in this direction this is the radius, no. So, at a small radius the nucleation will start at a particular degree of superheat. It will continue for up to this value of the radius, and then beyond that there will not be any nucleation. That means, very small aperture that will not give any nucleation, and very large aperture that will also not give nucleation. And you can see another thing, that as we increase delta T sat, so the cavity radius where the boiling will start, that goes on reducing, that more the temperature will increase. So, smaller and smaller cavities will get activated. Another thing we can see, that there is a particular radius beyond which no nucleation will take place. So, these all come from some theoretical analysis. This is approximate theoretical analysis, but from the theoretical analysis we all get this. Now, again there is one thing, as I have shown that we can manipulate the boiling curve here also there are some ways we can manipulate this curve, and by manipulating this curve my surface design I can do, so that I can get a good amount of nucleation. Sorry. So, this is taken from some literature. You see one is roughened by sandblast. So, this is roughened by sandblast. After that 2 and 3, if after sandblasting you oxidize it, then the again the roughness will reduce and we will get a lower degree of super boiling. Then if you use it for some time, after some time again it will reduce, and on the roughened surface if you put some wires etcetera, wire insert kind of a thing, then you will get very high rate of heat transfer. But if this surface is used for certain time, again the rate of heat transfer will reduce. So, the type of thing which we were talking, that aging, so that we can find. So, this is then surface roughness has been one way of increasing the nucleate boiling heat transfer, but thing is that we do not have much control over the surface roughness, because it is created by sandblasting or some sort of grinding etcetera. So, we do not have any control, but in general that increases the boiling heat transfer, and the increase is quite high. You can see that this is one value and this is another value. So, there could be quite large increase in the rate of nucleate boiling heat transfer. Sorry. Now, some in-house experience. So, this is more or less a commercial surface which is smooth, means whatever machining you have taken. So, which is smooth, and at a low temperature you can see that some bubbles have come as the temperature is increased. So, some bubble have come. This is from the MS work of one previous student Kumar, who is now faculty member in IIT Roorkee, and probably they are organizing the coming heat and mass transfer conference, which is our national conference and which is had got a very good international flavor. So, I tell all of you to look for it, attend or participate it if possible. Well, now what we have done, at regular interval we have put some sort of micro holes, very simple technique. By some sort of a small drill you put hole, and you see each and every point is a potential nucleation site. At a low degree of temperature, nowhere these vapor bubbles are there, but at the mouth of this radius we have got the vapor bubble. So, very simple technique, I mean has been shown that we can do it. So, this is your this is your plane surface. So, as we go on putting holes, our nucleate boiling heat transfer that increases, but again there is a law of diminishing return. More and more number of holes you put, you do not get first time the type of increase you have got, in second time you do not get that type of increase. So, that increase rate of increase decreases. Well, all right. Now, here we are showing the re-entrant cavity. How the re-entrant cavities are done? First thing you see, first example, re-entrant cavity or nucleation site artificially done. So, first example you see there is a fin. So, fin will obviously increase the area, but the fin will provide some sort of a corner. So, that corner is very good for bubble generation. So, the first example is simple fin, but that increases the rate of heat transfer. Then we have got porous layers. So, in the porous layer we will have different apertures and re-entrant cavity. Here the fins have been made, and after that they have given some sort of a deformation. So, we are having re-entrant cavity. These are all re-entrant cavities of different type, and this will increase the rate of heat transfer. Re-entrant cavities are not easy to form. Re-entrant cavities are different to, difficult to manufacture. So, people have thought of different kind of re-entrant cavities, And in heat transfer augmentation, one Professor Webb is no longer. So, Professor Webb has done lot of work, and single phase, both single phase, and he was actually an expert in multiphase heat transfer augmentation also, heat exchangers. So, he was in probably train for long, that refrigeration and air conditioning company. So, lot of work he has done. So, they have proposed something which is called tunnel and pore kind of geometry. What is a tunnel and pore kind of geometry? How they have done it? So, let us say this is a circular cylinder. On this circular cylinder, you have got two small fins. Okay. So, these fins, they will provide a long tunnel, and on this what they have done, they have put some sort of cellophane kind of a paper, and on this paper they have made small apertures at different places. So, you have got a tunnel and you have got a pore. So, basically then this is like this, you have got something like this. So, tunnel and pore geometry, and they have got model also for this. So, this gives lot of enhancement in heat transfer. So, we got certain hints that there should be some sort of a corner kind of a thing, there should be some sort of a re-entrant geometry, but re-entrant geometry is very difficult to produce. So, there should be some method of producing re-entrant geometry, and this kind of tunnel and pore kind of geometry could be one re-entrant geometry which we can put into use. So, now I will go to some of our experiment, some experiment I have shown. So, here there we have done very simple thing, that we have done drill, micro drilling, but here what we have done, we have used kind of tunnel geometry, and in these tunnel geometries have been done very I mean little bit intelligently, so that we get good amount of heat transfer augmentation. This is the setup, I will not describe the setup. Horizontal plate is there for boiling, and these tunnels have been made on copper plate with the help of wire EDM. So, this wire EDM setup is also, or wire EDM technique is also being shown here. So, this kind of geometries we have got. Okay, let me go to the previous slide. So, this is the setup, and by wire EDM we have cut this tunnel geometry, and then this kind of tunnel geometries we have done. So, simple tunnel, and this will give nucleation, but what we have postulated, that instead of simple tunnel, vertical tunnel, if we give them some angle of inclination, which I have given here, so that will give an enhancement in heat transfer, and that really gave. Then at the bottom of the tunnel, we have made certain features, which is not totally re-entrant, but to some extent it is bringing the attributes of re-entrant cavity. And then of course, this is parallel tunnel, and then we can have crisscross tunnel on the same surface to have more nucleation site. So, we have gone for this crisscross tunnel, and we have also made some sort of a nomenclature for this. I do not know whether it is visible or not. So, let us say this is unidirectional tunnel, vertical, so 90, then thickness and width, and then whether there is any bottom feature or not. So, these many different kind of surfaces we have made. These are the different surfaces you can see, and with this we could get a very good enhancement in heat transfer. Okay. Now, I have not shown the curves etcetera, because these curves are showing that when there is crisscross tunnels and with bottom features etcetera, these are published papers are there. So, it gives very good amount of heat transfer. Only see these are passive techniques, because the vertical tunnel, whatever kind of geometry is there, only you make it inclined, you get substantial increase in rate of heat transfer. But then let us try to go to some other aspect. The aspect, next aspect which I like to discuss, which I have hinted earlier also. Let us say in reduced gravity, you see boiling and condensation both are dependent on gravity, because another phase is formed and that phase has to move from the heat transfer surface. In case of boiling, due to either fluid motion or due to gravity, the vapor is going in the upward direction. Due to during condensation, whatever condensate is formed, so it has to fall, the surface should be again ready to take new fluid. So, otherwise we will not be able to sustain it. Now, in case of low gravity application, space application etcetera, that how one can do it. Obviously, it is very difficult, and people have postulated that other body force field, it could be anything, could be centrifugal field also, that can be used for removal of one phase or separation of one phase from another, because phases are having different densities. So, we have done a small experiment, the same thing, and at the top we have put some sort of mechanical stirrer. You see, when we put the mechanical stirrer, can you see there is a preferred direction of the bubble to release, and in this case it will be that you see from the surface it is almost coming in the vertical direction by this rotation of this one. Okay. So, this is at a low heat flux and this is at a high heat flux. This will be more clear if we go for even higher heat flux. You see how the bubbles are getting, I mean you can make the phase to come to one place and to circulate. So, two things we wanted to see here. One is some sort of hybrid augmentation, where you will have surface features plus you will have a rotating field, and that bubble release, whether it can be assisted by centrifugal field. So, both of these are coming in this particular thing. Of course, it needs more study that how the centrifugal field will be developed etcetera. It is a very crude experiment, but at least the proof of concept is given from this experiment. I like to discuss one or two things and then I will go to condensation. We are trying to make it short. So, we have got this thing that how boiling can be started earlier by making cavity, how boiling can be made, boiling heat transfer can be made more by again the cavity design or nucleation site design. Then critical heat flux, how we can improve critical heat flux. In fact, by providing gravity etcetera, critical heat flux increases, but whether there is any focused way of addressing the critical heat flux issue. Now, critical heat flux, I do not know whether it has been told or not, that in critical heat flux again the entire surface is almost covered with the bubble, and then the bubble has to release by some sort of jets or columns like this. And again if we see the top view, there will be columns formed like this, and through these columns the bubbles or vapor will release. Now, when they will release, the vapor phase will have some velocity, liquid phase will go in the downward direction, it will have some other velocity. So, there is a velocity difference. So, Kelvin-Helmholtz instability comes into picture, and these columns becomes unstable, and they also interact with the surround, I mean with the neighboring column, and then there is not a very good path for the liquid to go below, and then critical heat flux takes place, because the surface suffers from the lack of fresh liquid. Now, if we can provide some sort of a vapor path, so that they are not mixing with each other, liquid is getting a way to go in. So, obviously, people thought that this thing can be increased, critical heat flux can be raised. So, one example I show it here. So, this is from a thesis which has been done in Japan. You see, they have provided some sort of a surface, then on the surface they have put some sort of nanoparticle etcetera. So, that more vapor generation will be there. So, there is a porous layer. Okay. This will also enhance the heat transfer, but after that there is some sort of egg crate like structure which will give channels for liquid and vapor separately. So, this could be may not be touching the surface, but at the top of it, at the top of the surface you are trying to have a good path for liquid and vapor, separate path for liquid and vapor, they are not disturbing each other. So, critical heat flux can be raised. So, by some sort of remote, okay, it is quote unquote remote because it is not on the surface. So, you can enhance the critical heat flux. Another technique I will just tell and then we will switch over to, you see a liquid vapor contact is like this, and critical heat flux, during critical heat flux from the liquid to vapor generation, this is the path. So, Kandlikar in some of the work he has postulated that if we have multiple contact, so here the liquid and solid contact is here, but if we have multiple liquid solid contact, then the critical heat flux can be increased. How it can be done? Suppose you have got micro pillars etcetera. So, you have got two contact now, here one contact and here one contact and wedge shaped liquid. So, this will increase the critical heat flux, and he has shown that that can be done. So, I have discussed these three issues, how inception of boiling can be made earlier, how during nucleate boiling heat transfer can be enhanced, and how critical heat flux can be enhanced. So, probably engineering design is needed, and most of them are applicable for engineering, means large engineering surfaces, tubes, flat surface etcetera. So, probably if one can combine all these things, then a good amount of heat transfer augmentation is possible. Now, there are other aspects of heat transfer augmentation also by additive, already nanofluid I have discussed. I due to shortage of time I wanted to discuss that, but I will not do. Just quickly let us touch condensation. So, condensation has got two types of condensation, drop wise condensation. So, what can we do in case of drop wise condensation? Drop wise condensation is very good, very high rate of heat transfer. So, promotion of drop wise condensation, surface structure can be made such that it gives drop wise condensation. Droplets, there is not intermixing of droplet. Surface chemistry, changing surface chemistry also we can do that, structure and chemistry. Then the drops are to be removed, otherwise we cannot have drop wise condensation for a sustained period of time. Then drop wise condensation is not possible in all cases, big engineering systems it is not possible, we will have film wise condensation. So, if we have film wise condensation, then thinning of condensate film and draining of condensate film, that is very important. So, for heat transfer augmentation, if we need to have for condensation, these two things for film wise condensation we have to do. I will just show one example. These are called low integral fin tube. So, low integral fin tube is like this. Let me go back to my. So, let us say these are not basically fin, these are okay, increased surface, but not like fin. So, we have got this is the base surface and on the top of it we have this low height fins. So, condensation will take place here, very thin condensate, and then the condensate will get collected. So, basically I am getting some extra area for heat transfer, this is extra area for heat transfer, and this is also very important, where this is called garter through which the condensate film can be drained. So, basically I have to go for this kind of a design, and many commercial tubes are designed like this. So, that we have got garter and then low height fins, and we have high rate of condensation. Now, condensate draining is very important. Surface tension plays a very important role in condensate draining. again the surface of these fins, low integral fins, low height fins, they can be designed so that surface tension you are exploiting for the drainage of fin. There was one Russian scientist Gregory. So, Gregoric surface which looks like something like this. So, what is done in Gregoric surface? The surface is designed in such a way that the liquid surface tension is exploited, and everywhere, almost everywhere you get constant thickness of film. So, this is also one thing people try. Of course, these surfaces are difficult to do. I do not know nowadays, I do not find any interest, but I think smaller, see bigger larger pipe, these surfaces are difficult to do, but for smaller system one can again try this thing, but these have become, I mean it has gone to oblivion. People have probably forgotten regarding all those classical things what earlier used to be there. So, mainly for condensation we have got these kind of things, but some of the tubes which I have shown for boiling. So, those tubes are also used for condensation, and this is one example I like to show. This is some sort of a this is some sort of a desert beetle. They have got patches of hydrophobic and hydrophilic surface on their body. So, somewhere water is collected and then water is drained in preferential direction by having these patches. So, these type of surfaces particularly for micro scale systems, that is becoming very popular. People are doing different kind of experimentation with the combination of hydrophilic and hydrophobic surfaces. Somewhere water will be or rather liquid will form as droplet, but then they have to be drained and ultimately taken out of the surface. So, that is what is very important in case of condensation. So, I think that is all. I had something written, but already 1 o'clock. So, I will stop over here. If any question is there regarding the augmentation techniques, whatever I know, I will be happy to